Good morning. Today we are going to start discussion on a smart polymer which provides a response to a stimulus. It receives a stimulus and it gives some response. What kind of stimulus it may be? Those stimuli might be. So, it might be pH, acidity or alkalinity of a medium, temperature, pressure, electric field, radiation, etc. That means a system is called smart if it can receive a signal from a stimulus and it receives a response in the form of a signal, then it processes the signal and depending on the signal it actually gives again a function accordingly depending on the quantity of signal, amount of signal it has received. So, these are called stimuli responsive polymers. Stimuli is a plural form of stimulus. So, stimuli responsive polymers and gels. If the polymers are used in the form of three-dimensional network which can be hydrophilic, which can show hydrophilic, hydrophobic transition, phase transition with change in temperature, then those gels can find some suitable applications. So, stimuli responsive polymers and gels, and we can call these polymers as smart polymers. Okay. Now, these polymers are intelligent. A system is intelligent if it can recognize a signal and give a response to that signal. We can call it an intelligent system. So, these polymers can act as intelligent. I will give you the example little later. And these polymers find extensive use today in biomedical application. They have structures and functions of new intelligent materials which can be changed by external stimuli. Stimuli responsive polymers change their structure and properties under external signals. From this you understand they have certain specific structure, specific configuration in the molecule which is changed after receipt of the signal and then it functions accordingly. These polymers as intelligent materials which can respond to stimuli can be applied to drug delivery systems, DDSS, drug delivery systems and biomedical engineering systems. The materials that change their structure and properties in response to external chemical and or physical stimuli such as pH, light and temperature are called as intelligent materials. These materials can sense a stimulus as a signal which can be termed as sensor function. If it can sense a stimulus, say change in temperature or change in pH, okay, etc., then we can call it has got some sensing function or sensor function. Then it can judge the magnitude of the signal that is called processor function. So, sensor function, processor function which can judge the magnitude of the signal, and their functions in direct response. Accordingly, after recognizing the signal, it can start functioning, start changing its structure, and means either it can show some physical or chemical changes after receipt of that signal, that is called effector function. Now, these polymers permit external stimuli induced modulation of structures, stimuli induced modulation of structures. For example, say if it is hydrophobic in nature, it can be changed to hydrophilic, or if it is hydrophilic in nature, it can be changed to hydrophobic with a change in even 1 degree change in temperature. As a result of 1 degree change in temperature, it can show such change of phase or configuration, molecular configuration, hydrophobic to hydrophilic or hydrophilic to hydrophobic transition, and that can be exploited in various applications for various use. And since such changes occurs in a very small range of signal, it can be said on off switching device type of thing. Either it can switch on the system or it can switch off the system. For example, say we have pancreas. What is the function of pancreas? Function of pancreas is to sense the glucose level in the blood. If there is high level of glucose, say for diabetic patients, then there will be change in temperature of the body temperature, and accordingly pancreas has to give some command or release some insulin. That insulin will interact with this glucose, so that it maintains the normal glucose level in the patient's body. That is the function of the pancreas. So, if we can think of an artificial pancreas, that artificial pancreas, if it contains, if some insulin can be kept trapped in this artificial pancreas, and if that artificial pancreas contains such polymer, so with change in 1 degree or 2 degrees of temperature, so it can either release insulin or can stop releasing of insulin, so that the normal glucose level in the blood can be maintained and body hemostasis can be maintained to have the normal function of the patient. So, that is called on off switching your function of this device containing such polymer. Here it is written, artificial organs are needed to stabilize the body condition of a patient, say artificial pancreas for sensing the glucose level and respond to it by releasing or stopping the release of insulin. This development is an outcome of controlled release concept. This controlled release can be of great use in medicine, chemical, agriculture and cosmetic industries. In agriculture, what we do? We just spray some pesticide to stop the attack of pests, or we just apply this your fertilizer. What happens if there is water, if there is your flow of water, or if that the water holding capacity of the soil is not adequate, then if that water which dissolves this fertilizer can take away the fertilizer without being accepted by the plants, without being taken by the plant. So, there is loss of fertilizer, that means fruitful or efficient utilization of the fertilizer is not done. In order to avoid those problems, if there are certain devices available in which this fertilizer can be kept encapsulated, okay. From that encapsulated fertilizer device, if fertilizers are released slowly in regulated quantity, then the plant can take its fertilizer from that device and there is no loss of fertilizer. That means, with a smaller quantity of fertilizer we can get large amount of products. Okay. That is your fertilizer in case of agriculture. In case of drug delivery, what we do? Normally we incorporate the drugs through oral incorporation or by intravenous injection or intramuscular injection, what happens? The problem might be somewhere else, but the doctor prescribes a medicine which you swallow, it passes through the stomach to the intestine through colon, etc., and during which it is absorbed by the body. Now, there is a consideration of dose, amount of the drug which is required, and that picks up with the body fluid, and then it goes to the blood and it reaches the actual your affected site, target site. Now, the drug concentration which is required at the affected site, either it may be low or it may be high. Not only that, the other parts of the body might be affected by the drug. So, what we need? We need a real quantity of drug or actual quantity of drug. It should reach the target site and it should not affect any other parts of the body or any other organs of the body. So, for that today many people are trying to develop drug delivery devices which can be just carried to the targeted site, say tumor patients, say cancer tumor patients, malignant tumor patients. So, if the drug could be taken to that tumor site directly, so those your affected cells, tumor cells can be removed or can be cured, and this way tumor can be cured and cancer can be fought that way. But what is the device? How to do? So, chemotherapy is one of that. What is chemotherapy? Chemotherapy, some drug is incorporated in the body, and that is really painful affairs for the patient. Many patients cannot sustain the pain and the side effects of the chemotherapy, and ultimately, although even this your affected cancer cells are destroyed, but the patients cannot sustain the drug and the other side effects, so the patient dies. Now, today people have devised, say, parenteral drug delivery, in which such drug is encapsulated in the form of minute, very small dispersed particles known as emulsified drugs in a core cell morphology, in a core cell design. So, that drug is incorporated in the body through injection, intravenous injection, and it circulates and it keeps the drug in a stable condition without releasing in the blood. Only when that blood containing that emulsion, that drug reaches that affected tumor site, it will release over there. So, these are under research and people are developing, and it is being tried in animals. So, that is called controlled drug delivery. So, it should release the drug in real therapeutic level, therapeutic dose, not below, not above. That is called controlled drug delivery, targeted drug delivery, site specific drug delivery. You understand? Now, for that we need such smart system. I tell you one example, if possible I will cover that also later on. There is a system, say biodegradable polymer, in which some drug can be encapsulated. After that, that biodegradable polymer can be covered with a conducting polymer. Okay. So, that forms like a tube, nanotube, conducting polymer nanotube. The inside of the conducting polymer nanotube contains a biodegradable polymer which contains this drug. What is normally done? After drug loading into the biodegradable polymer, that conducting polymer is synthesized on that biodegradable polymer fiber. After that, the conducting polymer forms a coating over that biodegradable polymer fiber. Then the inside biodegradable polymer is degraded, leaving behind the drug within the conducting polymer nanotube. Okay. Now, that conducting polymer nanotube can respond to some electric field, positive potential or negative potential. So, after incorporation in the body, if from outside, if some potential is applied, positive voltage or negative voltage is applied, what happens? That nanotube, that your conducting polymer nanotube will either squeeze or reduce in diameter or expand in diameter. So, if it reduces its diameter, then the drug inside the nanotube will come out, drug release will be done. That is again a smart system. So, likewise here we can think of some polymer which can respond to some your temperature stimulus, heat stimulus, so that the change in temperature can change its conformation or configuration, by which either it can shrink or it can expand. Okay. That we are going to show you. Look at this polymer molecule. Molecule is not very complex. You see, you know this formula of this polymer. Okay. What is this? Polyacrylamide, isn't it? This is polyacrylamide. Okay. Now, if this polyacrylamide can be modified, that means if this hydrogen of this attached to nitrogen can be replaced with some alkyl group. So, that is here isopropyl group. Okay. So, here it becomes, if it is isopropyl group CH3, actually the polymer becomes N isopropyl acrylamide. So, the name of this polymer is poly N isopropyl acrylamide. If you just critically examine this formula and the structure of this polymer, you see, because of this oxygen and nitrogen, this polymer can show some hydrophilic property, and this portion and the backbone portion can provide hydrophobic property. Okay. So, it has been found that this polymer shows this polymer is water soluble. This polymer is soluble in water. What happens? There is a characteristic temperature at which this polymer shows some cloud point, that is called cloud temperature. Means it shows a change in phase. It comes out from the soluble phase to the insoluble phase, or that cloud point can be told as lower critical solution temperature. In other way, LCST. Below this critical solution temperature, it is hydrophilic. Above the critical solution temperature, it is hydrophobic. Now, in order to make this polymer hydrophobic, please look into this structure. In order to make this polymer hydrophobic, what you have to do? You have to hide this hydrophilic portion. Okay. If this hydrophilic portion is actually hidden, then it can show hydrophobicity. Now, that occurs if the temperature is increased. If the temperature is increased from LCST, become hydrophobic. hydrophobic. Now, if the temperature is decreased from LCST, it becomes hydrophilic. That means, in order to make this polymer hydrophilic, so this portion should be exposed. Again, if you want to make this portion of the polymer molecule to be exposed, so it should expand. It should expand. So, it shows expansion, it shows shrinking. So, the polymer either shrinks or expands. Shrinking due to assumption of hydrophobic configuration, okay, and expansion or swelling due to hydrophilic configuration. Swelling, you see, it is very simple, it is not very difficult. You see, for hydrophilicity, for swelling, this portion should get access to water molecule, isn't it? Water molecule should penetrate this site, then only it can show hydrophilicity. For that it needs expansion, swelling. Okay. Say if you keep your hand immersed in water, in a bucket of water, what happens? For say few minutes, you will find that your skin, both entire skin has got swollen due to water imbibition there, due to hydrophilicity of the tissue. So, that is hydrophilicity. So, water gets incorporated there and it swells. So, if water goes inside, it assumes it needs certain volume. So, because of imbibition or incorporation of water, so it swells the system. So, swelling, deswelling, swelling, deswelling, hydrophilic to hydrophobic. So, swelling, deswelling and hydrophilicity, hydrophobicity, these are related. Swelling means hydrophilic, deswelling means hydrophobic. Okay. So, this is a very simple property, but you see Professor Okano, he is pioneer, the credit should go to him, T. Okano. This is his work, this development or this discovery of this such type of system or polymer, credit goes to Professor Taruo Okano, Japanese scientist, he did it. Okay. Now, you see, poly N isopropyl acryl amide having a carboxyl group at one end. Now, you see here I showed CH2 CH CO N H and I should actually sorry. Okay. So, this is the polymer. Now, if this polymer could be attached onto a surface at one site like this, there are n units. Now, there could be some functional groups. In the previous slide you see these are the functional groups: carboxyl, amino, hydroxyl, reactive functional group. That could be attached here, say you write as X is the functional group. Now, these functional groups, the presence of these functional groups are required onto attachment to a surface. Suppose for cell culture containers, tissue culture dish. Normally we use polystyrene tissue culture dish, tissue culture plate. Now, if that polystyrene tissue culture plate surface is modified or covered with a thin layer of this polymer, then there is huge advantage of tissue culture and harvesting. We can get better confluence of cell growth and then excellent cell recovery and cell harvesting. Otherwise, normal way of cell harvesting is to treat with some enzyme, say trypsin. By trypsin treatment, the cells are actually removed from the culture plate. There actually it undergoes certain damage of the tissues and confluency of the cell is lost. Confluency, I will show you what is meant by confluency later. So, these are the applications. Not only that, in chromatographic system we will see that how it helps in artificial drug delivery systems, how it helps. So, for these purposes we need to attach one functional group, reactive functional groups at one end of the polymer chain, and we can regulate the molecular weight of the polymer chain by varying this n. Not only that, we can control this hydrophilicity or hydrophobicity. For this polymer, you can tailor its LCST to be say 32 degrees Celsius, 25 degrees Celsius, 22 degrees Celsius, 20 degrees Celsius or even 15 degrees Celsius. These are possible. How? That means at what temperature it shows this transition from hydrophobic to hydrophilic or vice versa. That depends on the frequency of this group. That means, if you make a copolymer of this monomer with another monomer, say butyl methacrylate or ethyl methacrylate, certain percentage of butyl methacrylate monomer is polymerized with N-isopropyl acrylamide monomer, or certain percentage of ethyl methacrylate is copolymerized with this N-isopropyl acrylamide. So, by controlling that copolymer composition, we can have a variation in LCST like this as we require, because it is not always possible that in all cases or in all devices, in all applications, we find that only one transition temperature it will show this transition. No, it is not necessary, it is not possible also, it is not required also. So, we have to see what temperature we need, what is the value of LCST requirement, LCST value, or that is what is the value of cloud point for that particular application. Thinking that, knowing that, we can synthesize, we can go for proper suitable synthesis for this kind of polymer preparation.
Shrinkage is due to the movement of methyl group.
Methyl group, that means not only the methyl group and also bending of this backbone chain. That means this portion has to be hidden. To hide this portion, to make it, to convert it from hydrophilic to hydrophobic, this portion should be hidden. So, this is not always possible with this isopropyl group. There is contribution from this backbone chain also. So, one could take other backbone, but why this backbone has been taken? So, here you see material surfaces can be modified, hydrogels can be modified, bioactive molecule can be modified. I understand, you understand what is surface. I mean, the surface of a body, we can characterize the surface of a body knowing the material surface, knowing the material made of it, either metal or wood or polymer or a ceramic. We know the composition, chemical composition of the surface, fine. But what is hydrogel? What is hydrogel? Now, you have certain confusion about gel. Okay. You put some solute in water in a solvent, if there is homogeneous mixing, if the free energy of mixing is negative, we find we can call is an ideal solution, is not it? That means, in ideal solution there is interaction between the solute and the solvent. And their free energy of mixing should be negative. And you know that can be measured with the help of solubility parameter. Free energy of mixing delta G is equal to, do you remember that relation?
Yes.
What is that relation? Related to solubility parameter. Isn't it? This is the solubility parameter of the two components. This is the volume fraction of the two components. One is the solute and the other is the solvent, and solubility parameter of the solute, solubility parameter of the solvent. And in this case, we can get an ideal or miscible solution, homogeneous solution, if this delta G is, value of delta G is negative, isn't it? Here also, say gel. What is gel? From solution phase, if the solutes are separated as a solid phase or comes out of the soluble phase, solution phase, we call it a precipitate, isn't it? We call it a precipitate. Now, that can occur in various ways. You change the temperature, there can be a change in phase, isn't it? You can find a solution at certain temperature that can reject some quantity of the solute if you decrease the temperature, or that can accommodate some more quantity of solute if you increase the temperature. So, there is a temperature at which it has a characteristic solubility. That from that point of view we can get the concept of solubility or definition of solubility. When we express the solubility value of a solute, we always mention the temperature, at what temperature this is the solubility. These are the things. Now, another thing can happen, that if the two solute entities, units can be linked, then the size of the solute is changed, isn't it? Am I right? You have started with some solute which has got some definite volume. So, units of those solute are having some definite volumes, when by some chemical reaction or something else like that, if there is some bonding, tying between the 2 units or 3 units or all the units, what will happen? The size of the solute is changed, volume of the solute is changed, solubility parameter of the solute is changed. Accordingly, what will happen? It will come out of soluble phase, solution phase. Now, this that say a solute remains, when it remains in solution, we call a sol, call it a sol. Now, if there is certain chemical change, if the solutes in the sol are interlinked in a 3-dimensional fashion, we call it gelation, gel formation or cross linking, then their solubility parameter changes and what happens? It comes out of the soluble phase, that is called gel, sol and gel. Say if you take a natural rubber, all right, natural rubber, then you mix with little amount of carbon black, intimately you try to intimately mix it, that means try to disperse these carbon particles in that natural rubber molecules. What will happen? Some natural rubber molecules will be occluded by the carbon particles, and some molecules will not be occluded, will not be accommodated. Then after such mixing, you put in benzene, and benzene has been found to be a very good solvent for natural rubber. So, the natural rubber molecules which are not been occluded by carbon particles, those will go into solution. That means, sol part goes into solvent, and the other part which are occluded, that means are tied with the carbon black, that will not go into solution. So, there will be 2 parts, sol part and gel part. This is one thing. Another thing, instead of mixing with carbon black, you mix with sulfur or other cross linking agent, small quantity, very small quantity, heat it. So, there will be some intermolecular linkage between natural rubber molecules through sulfur, and some molecules will not be linked. So, the molecules which are not linked through sulfur, that will go into solution in benzene, and the other portion will not go into solution, that is called gel. So, those 2 parts you can separate, just do the simple filtration using a filter paper. So, gel part will be separated from the sol part, that is called gel. Similarly, if you take the example of polyvinyl alcohol, you know polyvinyl alcohol, what is the formula of polyvinyl alcohol? How many persons can write? Raise your hands, polyvinyl alcohol. This side is very weak, polyvinyl alcohol. You? Pradipto, polyvinyl alcohol, could you hear me? Why you are not responding? Could you write polyvinyl alcohol? But why you are not responding? Either you can write or not. How do I understand that you can write? Sarda? Polyvinyl alcohol. My goodness. Many times I have shown this structure in the class. You remain sleeping. If you remain sleeping, you remain sleeping for the whole life. Okay. This is polyvinyl alcohol. This, because of this hydroxyl group, it is a hydrophilic polymer and is highly soluble in water. Okay. This is a water soluble polymer. When this water soluble polymer is reacted with glutyraldehyde, Ga, glutyraldehyde, it form cross linked polyvinyl alcohol, PVA, polyvinyl alcohol, or sometimes it is written PVAL, small l, PVAL. Okay. This is glutaraldehyde. This cross-linked polyvinyl alcohol means it can have configuration like this. Okay. In 3 dimension, I have shown in 2 dimension. In 3 dimension, it will have a 3-dimensional network of polymers interlinked through these bonds. Glutaraldehyde is present in these intermolecular bonds. This is a PVA gel, all right, PVA gel. This is a gel. It will not go into solution, but it will swell. Means why? Now, the segments, the length of the segment between the interlinkages, that depends, that actually controls this extent of swelling. That means, this volume, this space called free space available for accommodation of water molecules. Now, if there are few more bonds, total quantity of water accommodation will be further restricted. So, extent of swelling will be less. So, more swelling means light cross link is there, less swelling means you have more cross links. That means you can say in terms of cross link density. So, there is gel. So, the controlling the cross link density of gels, we can control the swelling, deswelling characteristics of a gel. Now, here you see the surface, here you see one surface represented by this portion, this surface is modified or surface is coated with such N-isopropyl acrylamide polymer. Okay. Now, 2 cases are shown over here, one case, this case. Now, when the temperature is increased, if the system temperature is increased, you see there is shrinkage of the molecules which are attached to the surface. When the temperature is decreased, the molecules, this shrinkage is obtained and it is expanded and it shows, say, swelling behavior. So, this is called hydrophilic, because this occurs by virtue of the hydrophilic nature of the polymer, and this occurs by virtue of this hydrophobic nature of the polymer. So, here we see this is equilibrium situation or transition from hydrophobic to hydrophilic and hydrophilic to hydrophobic due to change in temperature. So, it is sensitive to change in temperature. So, we can say this as thermoresponsive. It respond to change in temperature. So, we call it thermoresponsive. Now, the same thing has been extended to hydrogels. You see, this is hydrogel. You see, these lines are polymer, represented by polymer. These are polymers. So, like this, these are polymers represented by polymers, where the linear molecules are interlinked through these bonds. Now, onto their surfaces, smaller these lengths of these thermoresponsive polymers are linked, modified. So, this gel has become thermoresponsive. That means, with change in temperature, it can either swell or shrink. Now, you think if some drug molecules could be incorporated inside this space, then as a result of change in temperature, either it can squeeze or it can swell. So, by this swelling and deswelling phenomena, it can release drug. Concept is very good. Now, you have to regulate how to release the drug, at what temperature, it should release the drug. Okay. But following this concept, that depends on the skill of your hand. How can you, how you have made this hydrogel and drug incorporation, drug loading. Today such type of things are available commercially also. Then bioactive molecules. Now these are bioactive molecules. Now these bioactive molecules, these are very much sensitive to temperature and solvents, etc. So when some process is done on bioactive molecules, there is every chance of denaturation of the molecules. Say in protein synthesis, in protein preparation, in protein isolation, in protein purification, or albumin, or many bioactive molecules which are very active. Okay, by small change in temperature, by small change in your chemical composition, pH, etc., there is denaturation of the system. So that should be prevented. In order to prevent that, or in order to say, if you want to separate such sensitive bioactive molecule from a solution, or from a process, following a process, then if such bioactive molecules could be tagged with, or such stimuli responsive polymers can be tagged to with these biomolecules, attached to biomolecules, then by change in temperature, you see it becomes, these bioactive molecules become insoluble. Although it is soluble, bioactive molecule is soluble, it cannot be made insoluble, but by attaching this molecule, such temperature change in temperature can make this bioactive molecule insoluble, and you can easily separate it. Okay. So these concepts are extended to modification of material surfaces, modification of hydrogels, modification of bioactive molecules. These are the concept. Now let us see some applications. Applications of stimuli responsive interfaces as molecular valves, filtration, separation, all these things. Purification. In the laboratory, you have used filter paper, you know filter paper. In industrial practice, filtration cloth is used. Filtration is one of the unit operation in chemical engineering. Separation, purification by filtration. Now there are certain restrictions, regulations which one should follow, otherwise proper separation, purification cannot be done. It has been found that if we can make a filtration bed which can provide this molecular valve. If there are valves, you open the valve, fluid will pass through, close the valve, fluid cannot pass. Could you tell me one example of a molecular valve available, used in the laboratories? Have you not heard? Have you not read anywhere? Yes, molecular sieves. Molecular sieves. Molecular sieves are used as molecular valves for purification, filtration, etc. Sometimes these molecular sieves are used as catalyst carriers. Those are porous. Molecular sieves are porous supports, porous entities which have got sufficient surfaces there onto which some surface active process can be carried out. Anyway, such molecular valves can be prepared, can be developed by these thermoresponsive polymers. You think of a porous bead, porous bead. Now, those who have seen the chromatographic separation and purification, column chromatography in the laboratory, column chromatography. What is that? A big column is taken and that column is filled with a packing material, that means it has a packing stationary bed. Stationary bed is made of particles or beds that might be porous or non-porous, both. Their surfaces are active, all right. So, from one end of the column, if you put a mixture, then slowly it mixture passes through the bed, and by virtue of the surface activity of the beads as well as the mobile phase, there will be partition of these solutes. In certain quantity goes remains in the mobile phase, certain quantity is temporarily bound with the active surface of the packing material. This is the principle. This way very sensitive things are separated, small quantity of material is separated, an important component is separated from unwanted things. And this is the way how to purify these drug molecules or any other active molecules. So, today we are consuming drugs, we are swallowing drugs that contains few milligrams of the actual active drug, that should be pure enough. Now, that drug is a chemical compound that is synthesized through chemical process. Once a drug is prepared through some chemical reaction involving some reactants, so the drug which you want to prepare can be the major component or the most important component. Along with this, some byproduct molecules are prepared are formed. So, you have to purify that drug, isn't it? You have to purify that drug. For that purification, you have to apply stringent conditions or stringent processes, which is expensive too. So, that drug might contain few percentage of impurities, say 2%, 3% impurity may be there. Now, that 2%, 3% impurity cannot be removed by common separation techniques. For that, you need to have your say this chromatographic separation, which can give you purest form of the drug, all right. So, this is the way. So, there the particle or bead you have taken, if it is porous, what happens? Both the mobile phase, say solvent, will pass through those pores as well as the drug molecules, or that component, active component can go through the pores of the bead or outside the pores of the bead. Say if the beads are particles are spherical in nature, so after packing what will happen? You just imagine a column packed with spherical balls. So, there will be some interspherical spaces, intersphere spaces, isn't it? Those are free. Through those spaces, these solvent molecules and the solid molecules will pass, as well as those passes through the beads, the porous volume of the beads. That principle has been exploited in gel permeation chromatography, GPC. All right. Now, if those beads are modified with such polymers, what will happen? So, that can work like a valve, function like a valve with change in temperature. So, if the surface of such beads are modified with these polymers, that can open the mouth of the pores or close the mouth of the pores. That way, either it can allow the component to pass through the pores, or it can stop the passage of the component through the pores. This is the principle. So, here when a stimuli responsive polymers are grafted onto porous membrane surface, the polymers act as molecular valves responding to the external physical and chemical stimuli and achieving controlled solution permeation. Examples are temperature responsive drug releasing nylon capsules on which this PIPAM chains are grafted. This system suppresses the release of sodium dinaphthalene sulfonic acid, which is a drug, above the cloud point of PIPM. Cloud point means that is LCST, local, your lower critical solution temperature. Cloud point means above such temperature it becomes cloudy, solid phase separates out. Below the temperature it becomes soluble, transparent. Above the temperature it becomes cloudy, below that temperature it is transparent. All right. So, at lower temperature ion formation is greatly enhanced due to hydration of PIPM. So, try to correlate and understand this concept. With the help of that concept, you see, beyond above the cloud point it does not permeate, below the cloud point it permeates. So, above the cloud point it closes the valve, below the cloud point it opens the valve. PIPM grafted polyvinyl fluoride, PVDF, polyvinyl fluoride, again this is a smart polymer, porous membrane which controls filtration rate. PVDF is also piezoelectric in nature. Thank you.